Hi, in this video we're going to be doing another example on buffer solutions, and except this time I'll also show you what the common ion effect is. Now let's show you an example of a common ion effect. We have HF aqueous forming H plus plus F minus, right? When you're adding to water, it's basically plus H2O, and this will turn into H3O plus. So HF aqueous plus H2O liquid forms H3O plus F minus. These two equations are essentially the same thing, and you can use either one. I just like to use this one because it shows me the water and the H3O plus, which I know, which this H3O plus helps me identifying it's an acid. Now, what if we add NaF? What if we add sodium fluoride? What will happen? The NaF will dissolve and it will turn into Na plus and F minus. Na plus is a weak conjugate acid of a strong base. So NaF will have no affinity for water and will remain as a spectrum. So the only thing that will be within the reaction is our F minus. F minus is a common ion in the solution. Now, Le Charlet's principle states that the reaction will proceed left to use up the excess F minus. And since it moves left, the pH will decrease, right? Since we're adding NaF, we're producing more F minuses because Na pretty much doesn't count. And since we're producing more F minuses, the reaction will shift this way. And if it shifts this way, that means there will be less H3O plus, which means the pH will increase. Now let's prove it. So let's say find the pH of 1.0 molar of HF. Now this is pure HF. When combining with water, this tells us the original pH, right? When you're asking to find the original pH, as we learned in the last unit, we just simply add it to water. So HF plus H2O, and we're gonna have our same reaction as above, H3O plus F minus. Again, if you use HF plus, if you just simply use HF forming H plus and F minus, that is also correct. Anyways, for over here, it told us we have 1.0, and when we're finding pH, we always use right chart. So we have 1.0 minus x, 1.0 minus x, H2O we don't count, 0, 0. There's going to be plus x, it's going to be x, x. K of HF, because we're producing H2O plus, we can use a K for HF. Let's see, K for HF is 7.2 times 10 to the negative fourth. 7.2 times 10 to the negative fourth, which will be equal to x squared divided by 1.0 minus x. So this K is small enough for us to ignore the plus and minus x, so we can ignore this. And over here, we delete the minus x as well. So now we can simply do 7.2 e to the negative fourth times 1.0 and take the square root of that, which will give us an x value of 0.0268. Now, negative log of that, because x is a concentration of H3O plus, which means negative log of that will be the pH, so negative log will be 1.57. 1.57 is our original pH of only HF. Now, time to add our NaF to it and see what happens. Now, after we add NaF, because we are producing F minus, we can use the same exact equation. We do not need to use the RBC chart. When we're adding a different form of solution, then we'll need to use the RBC chart, and I'll show you how to do that in the next few videos with more examples. So first, since we're producing HF, our production of HF matches perfectly into this right chart already. So we can just continue using this chart. HF plus H2O forms H3O plus F minus. Now let's say we're adding 1.0 molar of NaF into the solution. Alright, because we're adding NaF, the Na will not be counted, our F will straight up be added over here. So we don't need to look at this chart anymore. This chart only purpose is to tell us the original pH, which is 1.57. Alright, now we're going to take a look at the new chart. Our original concentration of HF did not change. Adding our base didn't change the original concentration of HF. So our original concentration of HF is still 1.0. Now we're also adding 1.0 molar of NaF. So this, instead of starting with 0, we're going to write 1.0 molar. Now, our concentration of H3O plus is still 0. And we'll now look at water. So this will still be 1.0 minus x. This will still be plus x. And this will be 0. This will be x over here. And this will be 1.0 plus x. And this time we can use the HH equation. For the HH equation, we're going to use pH is equal to pKa plus the log of conjugate base, which is divided by the acid. Now there is also a corresponding one that is for bases, and it's going to be the same thing. When you're dealing with bases, you're going to put the conjugate acid on top and base on the bottom. But so far we have all been dealing with H3O plus, producing H3O plus, so we're all dealing with acidic solutions. I'll show you examples of how to work with basic solutions in a future video as well. So now we have pH is equal to pK. So what is the pK going to be the K of? We have HF. So what is our Ka of HF? It's going to be 7.2 times 10 to the negative 4th. So pH is equal to the negative log of 7.2 times 10 to the negative 4th. Let me do that in short. Negative log 7.4, right? 7.2 e to the negative 4th will be 3.14. The negative log of 7.2 times 10 to the negative 4th is 3.14 plus the log of, let's see, our Ka is small enough to disregard this, and this. So it will be log of 1.0 divided by 1.0. Now, 1 divided by 1 is going to be 1, and 10 to the 0th power is 1, so this is technically 0. Log of 1 is 0. So we'll cross this out. So cross this out and replace it with 0. And now pH is equal to 3.14. This shows how we have an increase in pH. We're from 1.57 to 3.14. And this is a common ion effect. When we're adding its conjugate base, our pH will raise. And I showed you how to use proper rice charts to solve for the new pH. Thank you for watching.